Today we will solve the geodesic problem on a sphere using calculus of variations. We will derive the full mathematical relations and show why the shortest path on a sphere is a great circle. First, let us visualize the problem. We have a sphere and 2 points on its surface, point A and point B. A geodesic is the shortest path along the surface connecting these 2 points. We will compare a curved path that is not shortest and the true geodesic, which will turn out to be a great circle arc. To compute the shortest path, we need the arc length on a sphere. We use spherical coordinates. Radius are polar angle theta and azimuthal angle phi. The Cartesian coordinates are given by x equals our sine theta cosine phi, y equals our sine theta sine phi, and z equals our cosine theta. The arc length element on the sphere is ds squared equals r squared times d theta squared plus sine squared theta d phi squared. Now we build the functional to minimize. The path length s is the integral of ds. Using a parameter lambda, we get s equals r times the integral of the square root of theta dot squared plus sine squared theta phi dot squared d lambda. The Lagrangian is the square root expression. Because the Lagrangian does not explicitly depend on phi, its conjugate momentum is conserved. This gives a constant k equal to sine squared theta times phi dot divided by the square root of theta dot squared plus sine squared theta phi dot squared. It is convenient to use arc length s as the parameter. Then ds over d lambda equals r times the square root term. And we can rewrite the conservation law as sine squared theta d phi over ds equals k. Also, because s is arc length, the speed along the surface satisfies 1 equals d theta over ds squared plus sine squared theta d phi over ds squared. Now we combine these equations to eliminate d phi over ds. Solving for d phi over d theta gives a first-order differential equation. We get d phi over d theta equals k divided by sine squared theta times the square root of 1 minus k squared over sine squared theta. Integrating this differential equation yields the geodesic equation. The result can be written as cotangent theta equals a times cosine of phi minus phi naught, where a and phi naught are constants fixed by the 2 endpoints. Let us interpret this equation in 3 dimensions. Using x equals our sine theta cosine phi, y equals our sine theta sine phi, and z equals our cosine theta, we can convert the relation to a plane through the origin. The result is a linear equation, ax plus by plus cz equals 0, which is the equation of a plane passing through the center of the sphere. The geodesic is the intersection of this plane with the sphere, which is a great circle. So the calculus of variations shows that the shortest path on a sphere is the intersection of the sphere with a plane through its center. That intersection is a great circle, exactly the green arc on our diagram. Final result, the geodesics on a sphere are great circles. We derived the full variational equations, the conserved quantity, and the plane relation that defines the geodesic. This is why airplane routes and the shortest paths on Earth follow great circle arcs.
Don't forget to like this video, share it with your friends, and subscribe to Knowledge Station. Thank you for watching.